Hello and welcome back. In section 1.2, we'll be working with subsets and terminology. So we'll start with another definition. So set A is a subset of set B if and only if. You'll sometimes see mathematicians abbreviate that phrase to IFF. So if you're reading a math paper and you see IFF, they usually aren't giving you a typo. It's an if and only if statement. So if and only if every element of set A is also an element of set B. So what this if and only if statement means, it's basically two if-then statements put together. So this is basically two parts. So part one of this if and only if says that if set A is a subset of set B, then every element of set A is also an element of set B. And part two of the if and only if then says if every element of set A is also an element of set B, then set A is a subset of set B. So it's basically two if-then statements put together. So we use if and only if, meaning both the red and blue parts are true. So if you have one part, you have both parts. The notation for this, we're saying A is a subset of set B. We have what looks like sort of an extended C, or like a capital U turned sideways with a line under it. So this in words would be read A is a subset of B. Now we have a corollary to this definition. All a corollary means is an immediate result. It's basically no extra work to get this other property out of a mathematical idea. And that is that the empty set will always be a subset of set A, and A is here any set that you want. So whatever the set, the empty set is a subset of that set. So no matter how big A is, how small A is, could have no elements, a billion elements, the empty set is going to be a subset of that set. To prove it wrong, basically you would have to find some element of this set that is not found in this set, but this set by definition has no elements, so we'll never be able to do that. We'll never be able to prove it wrong. We have another corollary. Any set will be a subset of itself. So for example, if we let set A contain elements, we'll just say 1, 2. Well, then by definition, A again would just contain 1 and 2. So this is claiming that each element of this is contained within this, and that's true. 1 is in set A, 1 is also in set A. 2 is in set A, 2 is also in set A. There's nothing here that isn't covered there. So any set is a subset of itself. So that's two nice, pretty corollaries. The empty set is a subset of any set, and any set is a subset of itself. Next, we get into the idea of proper subsets. So A is a proper subset of B if and only if, so we have the two directions again. Every element of A is also an element of B. And, so we do have to meet both conditions when we say and A is not equal to B. Alright, so let's look at a handful of sets and we'll decide if these are true or false. So for these next few examples, set A will be defined as 1, 3, 5, and 7. Set B will be defined as 1, 3, 5, 7, and 9. Set C will be defined as 7, 5, 3, and 1. And set D will be defined as 1, 2, 3, and 4. Before we get to that, let's finish with our notation as well. Notation, if A is a proper subset of B, we just don't have the line underneath. So this would read A is a proper subset of B. Alright, so we'll decide if the following statements are true or false, and if they're false, we'll have to show why. So the first part of each of these problems is going to be translating the symbols into words in your mind. So the words that you should be hearing when you see this collection of symbols would read A, or set A is a subset of set B. So for that to be true, every element of A must also be included in set B. So we'll look one at a time. 1 is in set A, it's also in set B. So far, so good. 3 is in set A, 3 is also in set B. So far, so good. 5 is in A, 5 is also in B. 7 is in A, 7 is also in B. So this one is true. So then we'll check, is A a proper subset of set B? Well, we know we have the first part of the proper subset definition. We already checked, since we found that it's a subset, that every element of A is also an element of set B. The last thing we have to do is then check, if we want to see that it's a proper subset, is that the sets are not equal. So in other words, B has to have at least one element that A didn't have. B has element 9, A does not have element 9. So the sets are not equal to one another, but each piece of A is also in B. So this one is true. Every element of A is an element of B, but A and B are not equal sets. All right, so next we'll see, okay, is B a subset of set A? So again, make sure that you're working on getting the vocab down and able to translate these symbols into words in your mind. So for this to be true, every element of B has to also be an element of A. So we're okay on the 1. 1 is in B, 1 is also found in A. Checking the 3, 3 is in B, 3 is also in A. 5 is in B, 5 is also in A. 7 is in B, 7 is also in A. 9 is in B, 9 is not an element of A. So this one is false, and to prove why, I would just say that 9 is an element of B. 9 is not an element of A. So this symbol you'll recall from our work in 1.1. So next we'll check this. So hopefully in your head, in words, you read that as B is a proper subset of A. So when we don't have the line underneath, they're saying proper subset. Well, here, if it wasn't a subset to begin with, it can't be a special kind of subset. It's akin to if I told you that a car is not a Chevrolet, you don't have to ask me, is it a Corvette? A Corvette is a type of Chevrolet, so if it's not in the bigger category, it's not going to be a special kind of subcategory. So here all we would have to say is that this is false, and for our explanation we just say that B is not a subset. So here's the subset symbol, just a slash through it means is not a subset. B is not a subset of A, and that's sufficient to show why this is false. Alright, so I'm going to put up a few of these so we can play with some more of the sets. So I'm going to put them up and I'll ask you to pause the video, try them out, decide if they're true or false, and if they're false, show in symbols why they are false. So we'll try A is a proper subset of C. Is a subset of C. Next we'll try proper subset. A is a subset of C. A is a proper subset of C. Okay, so give those two problems a try. Go ahead and pause the video. Okay, welcome back. So part 1, we're claiming that A is a subset of set C. So in this one, I want everything in A to also be found in C. So 1 is in A, 1 is also in C. So far, so good. 3 is in set A. 3 is also in set C. So far, so good. 5 is in set A. 5 is also in C. 7 is in A. 7 is also an element of set C. We're good on that. That one was true. Then we want to know, okay, well, is it a proper subset? So proper subset, the only extra hurdle we have once we figure out that it is a subset, they can't be equal, but notice here the sets are equal. They have exactly the same elements. 1 is in both, 3 is in both, 5 is in both, 7 is in both. Neither one has one thing that the other does not have. So this would be false since A is equal to C. So that would be your reasoning. A is equal to C. C is a subset of set A, so now everything that's in C, I have to be able to find an element like that in A. So 7 I can find in A, 5 is in C, 5 is also in A. 3 is an element of C, 3 is an element of A, so far so good. 1 is in C, 1 is in A, that one is true. And the last one is false for the same reason as before. If one is going to be a proper subset of the other, they cannot be equal to one another, and here they are equal. So problem 2, we're working with B and D here. So we want to know, is B a subset of set D? So 1 is in B, 1 is also in D, so far so good. 3 is in B, 3 is also in D, so far so good. 5 is in B, 5 is not in D, so that one is false. All I have to do is find one element. There might be 10 elements or 100 elements that are in set B, not found in D. All I have to do to show it's false is show one of them. So 5 was the first one I ran across, so that is the one I'll list. So 5 was an element of B. 5 was not an element of D, which would make our next one false as well. You can't be a proper subset if you're not a subset to begin with. So B was not a subset of D. Next, we check it the other way around. We spin it around. So we see if D is a subset of B. So 1 is in D, 1 is in B, so far so good. 2 is in D, 2 is nowhere to be found in set B, so this one is false as well. Different reason than the first part of 2 though. So on this one, it was the element 2 that gave it away. So 2 was an element of D, 2 was not an element of set B. And the last one, false as well. If it's not a subset, it cannot be a proper subset. So D was not a subset of B. One other thing I want to point out before we move on to our next batch of examples. Notice the order is important here. A was a subset of B was true, B was a subset of A was false. The order on these is important. We're always reading them from left to right. Set listed to the left is a subset or is a proper subset of, and then whichever set is listed to the right. The order does matter. Now, one common thing to clarify at this point in time with respect to the notation and things like that and work with set theory is the idea of an element versus a subset. So for this one, we'll work with a new collection of sets. So R will contain elements A, B, and C. T will contain X, Y, and Z. I write my Z's a little bit different after teaching math for a lot of years. Answering the question too many times in an algebra course, was that a Z or a 2 when I wrote my Z's this way? If you put the slash, you don't get the is that a 0 or 2 question anymore. So my Z's all have the extra slash in the middle. Set V will contain elements B and A. Alright, so our first plane, and I'll write it in symbols and give you a second to see if you can say it in words in your mind. So this is saying set R is a proper subset of set V. So let's see if this is true. So first, if I want to see if it's a proper subset, I want to see if it's a subset at all. So A is an element of R, A is an element of V. So far, so good. B is an element of set R, B is an element of set V. So far, so good. C is an element of R, C is not an element of V. So this one would be false. So our reason was element C. So C was an element of R, C was not an element of set V. But let's try flipping that around. So see if you can convince yourself if this is true or false. Okay, so in words, hopefully you figured out that this is set V is a proper subset, no line underneath means proper subset of set R. So that means everything in V has to be found in R, that makes it a subset, and V and R can't be equal. So B is in set V, B is in set R. So far so good. A is in set V, A is in set R. So far so good. So it is a subset. Now we want to see, is it that special kind? Is it a proper subset? Are the sets not equal? They are in fact not equal to each other. R contains element C. V does not contain element C. So this one is true. Now something else that will get some students mixed up though. V is an element of R is what this is claiming. But if you look at set R, remember this symbol means is an element of. V is not one of the things listed here in the list of elements of set R, so this one is false. So really in symbols, we don't really have any more explanation than just saying it is not an element. They use the wrong symbol. This one would read X is an element of set T. That is true. But if they said X is a proper subset of T, that is false. X is an element, not a set. So X is an element, not a set. So these two symbols, not interchangeable. They do mean different things. Is an element of, is a proper subset of. Two totally different ideas. But one thing they could do to sort of change this up a little bit on us, set X is a proper subset of T. So that means that I have to check and see that everything in this set is also contained in set T, and that this is not equal to set T. So the only element I see here is X, and X is within set T, so far so good. And this and T are definitely not equal to one another. T has a cardinality of 3, this has a cardinality of 1, so this would actually be true. So it makes a difference, are we listing the element by itself, or did we put the element within a new set? All right, so some terminology. A complement. So we'll set the scenario first, so we'll let A be a subset of universal set cap U. So in symbols, A is a subset of the universal set. The complement of A they denote it A prime. Just as a heads up, some authors will use A with a bar over it. We'll be using the prime notation. Complement of A, denoted A prime, is the set of all elements of U not found in A. All right. Couple quick examples here. We're going to let U equal the letters of the alphabet. So A, B, C, D, E. And we'll put an ellipse there. Remember, the ellipse just means this pattern keeps happening. And we'll stop it at Z. And we have a comma in front of and behind the ellipse. We'll let A for this example. A, B, C, D, E, and we'll continue that pattern until we reach X. So U is all 26 letters of the alphabet. Set A goes A through X and then stops. So for this one, A complement will describe anything that is a letter of the alphabet other than things found in set A. So that means everything from A, B, C, D all the way through X is out, but Y is part of our universal set and Y is not part of A, so that is going to be in the complement. Same thing with Z. Z is not part of set A, but it is part of our universal set. Let's see. Look at another one. For our next example, our universal set will be the set of whole numbers. So recall the whole numbers started at 0 and then included the counting number. 0, 1, 2, 3, 4, as high as you want to go. It goes on forever. So no fractions in between, no decimals in between, just the nice, neat, pretty counting numbers and their buddy 0. That is the whole numbers. And for this problem, set B, we'll get a little practice done with set builder notation. That's going to be the set of all x such that x is in the set of whole numbers and that x is strictly greater than 5. So what I'm going to ask you to do before we get into the complement here is I've given you the set builder notation. I want you to pause the video and do the roster notation of set B. Okay, welcome back. So the roster notation of set B, well, let's look at our instructions, how we set up B. So x has to be in this list of whole numbers, but it has to be bigger than 5. So that means I can't include the 5, but 6 works. 6 is bigger than 5. 7 is bigger than 5. 8 is bigger than 5. 9 is bigger than 5. 10 is bigger than 5. And we could just keep going forever. So if you want a roster notation, this is the roster notation of B. So these are two different ways to identify the same set. So then let's look at the idea of the complement. So I'm looking for complement again. We're going with that prime notation, B prime. Things that are in the set of whole numbers other than what's on this list. So that means I would have everything lower than 6 but still in the whole numbers. So that would cover 0, 1, 2, 3, 4, and 5, but 6 is in set B, so it can't be in B complement. 7 is in B, 7 can't be in B complement, and so on. Now I could also have listed that in set builder notation. So B complement I could have described as the set of all x such that x is in the set of whole numbers and x was less than or equal to 5. Again, two different ways we can write it in roster notation or set builder notation. So I'm going to have you all try one out. So your universal set will be the single digit numbers in the Hindu Arabic number set. So 0, 1, 2, 3, all the way up through 9. And set